Welcome to today's paper reading. Today's paper is titled, Self-Rewarding Language Models. This paper was published on the AR14 preprint by Weizhe Yuan and colleagues from Meta and NYU. To achieve superhuman agents, future models need superhuman feedback to provide an adequate training signal. Current approaches, which train reward models from human preferences, are limited by human performance levels and cannot improve during LLM training. In this work, we explore self-rewarding language models, where the language model itself provides its own rewards during training through LLM-as-a-Judge prompting. Our experiments show that iterative DPO training not only improves instruction following but also enhances the model's ability to provide high-quality rewards. Fine-tuning Llama 270B with our approach yields a model that outperforms many existing systems on the AlpacaEval 2.0 leaderboard, including Claude 2, Gemini Pro, and GPT-40613. This work suggests the potential for models that can continually improve in both instruction following and reward modeling. Figure 1 illustrates the process of self-rewarding language models, which involves two main steps. First, in the self-instruction creation phase, new prompts are created to generate candidate responses from model empty. During this process, the model also predicts its own rewards using LLM-as-a-Judge prompting. Second, in the instruction following training phase, preference pairs are selected from the generated data and used for training via direct preference optimization, DPO, resulting in model MT+1. This entire procedure can be iterated, leading to improvements in both instruction following and reward modeling abilities. Figure 3 illustrates the progression of instruction following ability across different iterations of self-rewarding models. Initially, the SFT baseline performs similarly to self-rewarding iteration 1, M1. However, significant improvements are observed in iteration 2, M2, which surpasses both M1 and the SFT baseline. The trend continues in iteration 3, M3, which demonstrates further enhancements, achieving substantial gains over M2 and establishing a notable lead over all previous iterations, including the SFT baseline. Table 1 presents the AlpacaEval 2.0 results, showing the win rates of various models over GPT-4 Turbo. The self-rewarding models, particularly iteration 3, M3, demonstrate significant improvement with a win rate of 20.44%, outperforming not only GPT-4 Turbo but also several models that rely on proprietary training data or targets distilled from stronger models. The win rates progressively increase from 9.94% in iteration 1, M1, to 15.38% in iteration 2, M2, and finally to 20.44% in iteration 3, M3, highlighting the effectiveness of the self-rewarding training approach. Figure 4 presents the AlpacaEval win rate breakdown across various instruction categories. The self-rewarding models demonstrate significant improvements in win rates across multiple topics. However, these models show less improvement in tasks related to mathematics and logical reasoning. The full names of the instruction categories are provided in the appendix. Detailed statistical information and prompting techniques used for this breakdown can be found in Appendix 8.6. Table 2 presents the empty bench results on a scale of 10, showing the performance of the SFT baseline and iterations of the self-rewarding model. The scores indicate that self-rewarding iterations yield improving scores across various categories. Notably, the math, code, and reasoning category shows smaller performance gains compared to other categories, which is likely due to the composition of the Open Assistant seed data used. The SFT baseline scores are 6.85 for overall, 3.93 for math, code and reasoning, and 8.60 for humanities, extraction, STEM, roleplay and writing. The M3 scores are 7.25 for overall, 4.17 for math, code and reasoning, and 9.10 for humanities, extraction, STEM, roleplay and writing. The scores improve across iterations, with M1 scoring 6.78, 3.83, and 8.55, M2 scoring 7.01, 4.05, and 8.79, and M3 scoring 7.25, 4.17, and 9.10. Table 3 presents the results of NLP benchmarks, showing that self-rewarding models generally maintain their performance levels compared to the Llama 270B base model and the SFT baseline. This is noteworthy as these models have been fine-tuned on significantly different instruction-following prompts. The table highlights the consistency in performance across various benchmarks, indicating the robustness of the self-rewarding models in handling diverse NLP tasks. Figure 5 presents the human evaluation results of self-rewarding models M1, M2, and M3, showing their progressively better head-to-head win rates against the SFT baseline. This aligns with the automatic evaluation results, indicating the effectiveness of the iterative training procedure. The introduction of this paper highlights the growing focus on large language models, LLMs, and their training methods. Specifically, it discusses reinforcement learning from human feedback, RLHF, where a fixed reward model is trained from human preference data and then used to train the model via reinforcement learning, such as proximal policy optimization, PPO. This approach, while effective, still relies on human data distillation. The paper also introduces reinforcement learning from AI feedback, RLAF, where an LLM provides feedback to refine responses, which is then used to train a reward model. This method is compared to RLHF and found to perform similarly. Additionally, the paper explores data augmentation techniques in LLMs, such as the self-instruct method, which creates training data to improve the base LLM. These methods, including distilling from powerful LLMs and instruction back translation, are crucial for enhancing LLM performance. Self-rewarding language models are designed to self-align by evaluating and training on their own outputs. This process is iterative, with each cycle involving the model generating preference-based training data. The model assigns rewards to its own outputs using a method called LLM-as-a-Judge prompting, and then trains on these preferences through Iterative DPO. The results show that this method enhances both the model's ability to follow instructions and its capability to model rewards over successive iterations. This creates a positive feedback loop where the model becomes better at assigning rewards, potentially leading to continuous improvement beyond human-defined preferences. The experimental results indicate that iterative training improves both the ability to follow instructions and the reward modeling capability. However, these results are considered preliminary due to the limited number of iterations conducted, specifically 3 in a single setting. Future research should explore the scaling laws of this effect across more iterations and with different language models. Additionally, the observed increase in the length of model generation suggests a correlation with estimated quality, which warrants further investigation. Safety evaluations are also a critical area for future study, particularly within the context of self-rewarding training processes. Utilizing the LLM-as-a-Judge procedure could help evaluate safety more effectively, potentially leading to improved safety over subsequent training iterations. In the related work section, we explore various strategies for self-correction in large language models. For instance, the paper AR14, 2308.03188 surveys diverse self-correction methods, while the OpenAI blog from 2019 discusses language models as unsupervised multitask learners. Another significant area is preference optimization, where papers like AR14, 2312.11456 and AR14, 2312.16682 focus on optimizing language models based on human feedback. Additionally, instruction-following models, such as those presented at ACL 2023 and the Stanford Alpaca Project, demonstrate advancements in aligning models with human instructions. These works collectively highlight the ongoing efforts to improve the performance and alignment of large language models with human expectations and requirements. Table 5 presents the results of various LLM-as-Judge prompts using a model trained solely on 3,200 IFT data. The table highlights that the additive score counting prompt significantly enhances EFT performance compared to the prompt used by Li et al. 2024. This demonstrates the effectiveness of the additive score counting method in improving the model's performance on EFT tasks. Figure 6 illustrates the distributions of instructions and responses across IFT, EFT, and AIFT data. The graph clearly shows that IFT and EFT data originate from distinct distributions, whereas IFT and AIFT data exhibit similar distribution patterns. This visualization aids in understanding the differences and similarities in the data sources used for various training methodologies. Figure 8 illustrates the impact of EFT data on the self-rewarding loop in model training. It shows that models M2 and M3, which were trained starting from a model using only IFT data, can improve over the SFT baseline. However, they significantly lag behind models M2 and M3, which were trained starting from a base model using both IFT and EFT data. This indicates that incorporating EFT data leads to superior performance in the self-rewarding loop. Figure 9 presents the prompt utilized to categorize instructions within the alpaca-eval test set. This prompt is designed to classify instructions into one of 20 high-level categories, ensuring a comprehensive and understandable breakdown of the instruction types. The categorization process is crucial for evaluating the diversity and complexity of instructions in the test set, providing insights into the types of tasks the models are expected to handle. Figure 10 presents a prompt designed to categorize instructions based on three key aspects: their topic, complexity, and the expected length of the response. The instructions are to be categorized into one of 20 predefined topics, scored for complexity on a scale from 1 to 10, and the length of the expected response is indicated, ranging from a single sentence to multiple paragraphs. This structured approach helps in systematically analyzing and organizing the instructions according to their nature and requirements. Table 6 provides a detailed breakdown of the alpaca-eval test set instructions categorized by their respective fields. The categories include science, technology, engineering, professional business, marketing, and social interaction, relationships, human behavior, among others. The data shows that science, technology, engineering instructions make up 16.65% of the total, followed by professional business, marketing at 9.57% and social interactions/relationships at 8.45%. This categorization helps in understanding the distribution and focus areas of the test set instructions. Table 7 provides a detailed breakdown of the alpaca-eval test set instructions categorized by their complexity levels. The complexity scale ranges from 1, representing the simplest instructions, to 9, indicating the most complex questions that necessitate preliminary reasoning or problem decomposition. Notably, complexity level 3 instructions constitute the largest portion at 29.57%, while the highest complexity level, 9, accounts for only 0.37% of the instructions. This distribution highlights the varying degrees of difficulty within the test set, reflecting a broad spectrum of instruction complexities. Figure 11 presents the win rate breakdown of self-rewarding models on the alpaca-eval test set, categorized by instruction complexity and expected response length. The left panel shows that self-rewarding models achieve significant gains across most complexity levels, indicating their effectiveness in handling a wide range of task difficulties. The right panel demonstrates improvements in win rates for all expected response lengths, from very short to longer responses, highlighting the versatility of these models in generating appropriate response lengths. Overall, the data underscores the superior performance of self-rewarding models compared to baseline models in various evaluation scenarios. Table 8 provides a detailed breakdown of the alpaca-eval test set instructions based on the expected response length. The data reveals that 44.84% of the instructions expect responses of 1 to 3 sentences, followed by 33.42% expecting a single paragraph. Additionally, 17.76% of the instructions require only a single sentence, while 3.85% and 0.13% expect 2 paragraphs and 3 or more paragraphs, respectively. In this study, self-rewarding models were evaluated for their ability to generate new prompts through in-context learning. Specifically, 30 prompts were constructed and tested on models M1, M2, and M3. The results indicate that all models can generate novel instructions based on in-context examples. However, for models M2 and M3, additional post-processing may be required due to the generation of separators. Additionally, the alpaca-eval test set was analyzed using the GPT-4 model to categorize instructions from 3 perspectives: instruction category, complexity, and expected response length. This categorization was achieved using a specific prompt, as detailed in the study. The study identified a total of 20 categories, which, while providing a structured framework, may limit the scope of the research and introduce potential biases. The clustering of instructions into different categories posed challenges, particularly in differentiating between similar instructions, which could impact the accuracy of the results. Additionally, general limitations such as resource constraints, time limitations, and the size of the sample used in the study further affect the overall robustness and applicability of the findings. Thank you for watching.